Hello. How's it going? Hope you're doing well and staying sane, as you can tell that I'm not. So today what we're going to do on Bed Talks here, we're going to talk about this ending part of basically vector calc and kind of calculus 3, and try to wrap it up in these next two videos, kind of try to close off a little bit more of that. And these two theorems that are going to come up, Stokes theorem and divergence theorem, are honestly some of the biggest theorems that we can really think about when coming to calculus 3. These are really powerful theorems and ways that kind of connect, hopefully, what we've been doing in calc 1 and kind of bridging it into these two kind of regimes here, especially in 3 dimensions. And this first part of Stokes theorem here is really, really beautiful. But to get Stokes theorem, we need to at least gain some more machinery before we can start to actually do some problems. So what we're going to do today is I'm going to explain what Stokes theorem is. We're going to do some problems too, probably 1 or 2 problems, to kind of show you how to use Stokes theorem, at least both ways, to kind of see what the problems are. And the first thing we need to do before we get to Stokes theorem is to first off understand, well, I have a vector field F, and I know to find out if it's conservative or not, right? There's a test I could find out if it's conservative or not. But what does it mean in 2 dimensions? But how do I do that in 3 dimensions? It's a little bit difficult. It's not as obvious as you would think, right? So let's assume that I have a vector field F here. It's just PQ. Right, what did we do? We assumed that, right, if this was a conservative vector field, it was related to some gradient, the gradient of f, which was fx, fy. And we saw that in order to see if this was a potential function, what we did was we kind of took the second partial derivative as the mixed partial derivative. So we would want to see if fxy is equal to fyx. Is this true? So that means I would need to take this derivative with respect to y and this derivative with respect to x. And this showed me that f is conservative. So as again related to Clairaut's theorem, which I kind of said that the mixed partial derivatives are the same if everything's continuous and everything's nice. But now, you know, what's interesting here is let's say now I have a vector field that's PQR. Maybe of three variables, right now of x, y, and z. And is this related to a potential function? Can I actually see that this is a potential function maybe of phi sub x, phi sub y, and phi sub z? How am I able to see this, right? How am I able to get that? Well, one way we can kind of see this is, well, I could still take second partial derivatives, and I know from Clairaut's theorem to have second partial derivatives that I'm going to need to, you know, in some way, have all of the second partial derivatives the same, regardless, right? So phi x, phi y has to be the same as phi y, phi x. Phi x, phi z has to be the same as phi y, phi z, and so on. So, you know, thinking about this, I need phi x, y to be equal to phi y, x. I need phi x, z to be equal to phi z, x. I need phi y, z, which one am I missing? Phi z, y, something like that here. And so if I assume that P is phi sub x, Q is phi sub y, and R is phi sub z, if this is going to happen, to have a conservative vector field, I need to satisfy 3 things. In this one, I had to just satisfy 1, right? Phi fxy was equal to fyx. So P is phi sub x. So for instance, here, this would be related to P sub y. And similarly here, phi sub yx, we're just taking the second part here, this phi y, with respect to x. So this would be just equal to qx. We actually, what's nice is this is the same condition that we have up here. Py is equal to qx. The x and y components just taking the derivatives individually. So now phi xz is actually taking p, right, with respect to z. And this q, and this zx is actually taking this r and taking this with respect to x here. Kind of like this. So this is another condition that I have to satisfy. I have to satisfy that this first component with respect to z is equal to this last component with respect to x. And lastly here, we have that phi sub yz, which is equal to this one, which is q sub z, has to equal, we get this one, has to equal r sub y. And if we satisfy all 3 of these conditions, then I can tell you that F is conservative. Otherwise, I can't. This means that F is conservative. Now, you might say to yourself, well, this is really tedious. Why would I memorize this? Why would I kind of do that? Yeah, you're right. It's very, very tedious. But what's really cool is that there's a calculation that we can do to quickly find out and kind of actually figure out if this vector field is conservative or not. But these are three conditions that are necessary to hold, and it kind of follows very, very quickly from Py being equal to Qx. And what's going to be really cool now is we're going to talk about something called the curl of a vector field. I'm going to define this for you, and then we'll talk about the kind of the aspect of it all and why we kind of define it this way. And well, it's actually defined kind of similarly for the reason that we see here. So we're going to talk about the curl of a vector field. The first thing I want you to know about curl, we also define it as this way: the cross product of this gradient vector and F here. We'll talk about that in 2 seconds. But basically what I'm going to try to say here is that the curl of this vector field is a way that we can check if a vector field is conservative or not. We'll kind of show you why. And this is related to the cross product of so the determinant of the following matrix. We have our I, j, and k vector fields. We then, in the second component, we are taking the derivatives with respect to x, y, and z. And then in the bottom part here, we have p, q, and r. And this right here is what we'll call the curl of a vector field. And why do we have the curl of a vector field? Well, let's just calculate this out really quickly. I think I'll show you what I mean here. How do we actually evaluate this thing? What does this curl actually mean? Well, first off, I hope you'd agree it's going to be a vector because we have the I, j, and k components. So it's going to be a vector. And so what we do is we take the I component here, we're going to take this determinant, which means that I'm going to take the partial derivative of r with respect to y. And then I'm going to subtract this from the partial derivative of q with respect to z. Just in a similar way that we would do in the past. But what I'm doing here is I'm actually saying that this is the derivative of r with respect to y. This is the derivative of q with respect to z, and so on. That's how I'm kind of reading this. The j component here, I'm now going to take the negative here, the negative right, to go out in front. The derivative of r with respect to x now, and the derivative of p with respect to z. And lastly here, this last component is the k component, which is q with respect to x minus p with respect to y. Or maybe you can write this more succinctly as ryqz pz minus rx, and then we have qx minus py. And this is what we will call the curl of a vector field. This is also another way you can write it. These two definitions are equivalent, as you can see. If you want to memorize this, go for it. This is much, much easier to kind of use on a daily basis, though. You don't have to memorize this. You just kind of set it up like this way and take the derivatives as is. We'll do some examples when we actually compute some problems here. But the curl of a vector field actually gives you some very, very interesting insight. Because I hope you'd agree, if I take the curl of this vector field, let's say my curl, let's say f is a conservative vector field. What would that tell me about each one of these components? Well, up here, we see all of the conditions it has to satisfy. If I satisfy all of these, well, if qz is equal to ry, would you agree this is 0? If pz is equal to rx, this is also 0. And lastly, if qx equals py, this is 0. Which is kind of cool. And so this actually means that this is going to be the 0 vector, or 0, 0, 0, if f is conservative. And so this is actually a really interesting way of seeing this. And so what's cool is, this means that f is conservative if and only if the curl of f is equal to 0. And it's very important that we keep this, at least here. So to find out if a three-dimensional vector field is conservative, we actually say this curl of f is equal to 0, specifically. Okay, so is equal to the 0 vector. You have to write the zero vector. It's not equal to 0 because curl is an actual vector quantity. And what does this vector quantity actually mean? What does this vector quantity mean? What does this curl of a vector field mean? Well, in some way, it's a way to how far away you are from being conservative, right? In the same exact way that we saw that Qx equal to Py was kind of that same exact thing relating to Green's theorem. But in this turn, we can kind of say that if I give you the curl of a vector field, we can talk about that as the rotation of the vector field. So given a quantity, if I tell you the curl of a vector field is a vector at some point, I give you the curl of a vector field. Let's say the curl is in this direction at this point, right? Kind of pointing out in this direction. It's going to be a vector. What that means, if I place an object here, if I place an object, what that means at that point, and I let the vector field kind of move it, just as it is, it will rotate around that axis in a counterclockwise manner. Okay, that's what it'll do. So if I place my vector field over here, or something like this, and my normal vector is this way, I place an object here, it will curl in this direction. So curl of a vector field actually gives me the idea of a rotation of a vector field. How fast is it rotating? How much is it kind of rotating here? And that idea is also related kind of heavily to what we think about in the two-dimensional case here. Because we thought about Green's theorem in some way, right? Where we saw that how I go in a counterclockwise manner, I could think about that, how the rotation is actually the inside and what that inside is actually entailing in that area. So this is what the curl of a vector field is. We'll talk about that in a little bit more, how to be calculated and all that. But it's just an important thing to at least realize here. Okay, so now we've gotten that out of the way. What do we do now? So this is the curl of a vector field. We can calculate it with this kind of form here. So what are we going to do now? What is Stokes' theorem saying? Well, I want to first off recall this integral that we were dealing with prior to this. We were dealing with some integral like this. Right? We were dealing with something like this here. Right? C, which was a curve that was closed and bounded. So C had to be closed and positively oriented. And positively oriented here again meant counterclockwise in some way, especially in 2 dimensions, right? That was counterclockwise with this, but positively oriented is going to be a little bit different here, especially as we go into higher dimensions. And we needed to have F had to be continuous in our domain D, right? So if I have my curve C here, kind of coming around this way, which is counterclockwise, this is my domain D, kind of like that. That's my goal. So I have that domain D. We saw that we could utilize Green's theorem here, which Green's theorem said I could change this integral, which sometimes also looked like, these are equivalent. I could change this integral to then say that this was equal to the double integral over my domain D of Qx minus Py dA. Where I could just kind of compute this area integral, which might be a lot simpler than a curve integral. Maybe either. I can even go backwards too, right? I can go backwards and forwards, kind of however I want to in this case. So with this in mind, we had this idea of Green's theorem, right? This is Green's theorem. I'm writing this in green for a reason. This is for the 2-dimensional case. Now, what if I had this in 3 dimensions? What if I did this in 3 dimensions? And I'm going to use purple for this one. And we're going to kind of now think about this in now. So I'm now going to try to calculate this, where F now is of 3 variables, of P, Q, and R. C is a closed positively oriented curve. Now, what does a positive orientation mean? And this is going to be a really important thing here because it's not totally clear cut in 3 dimensions what that means. But what I want you to kind of visualize is as follows. What positively oriented means is that it's kind of highly related to the surface I cover, okay? And we're going to need this, we're going to need S here. S is going to be my surface. So I'm going to try to draw this as best as I can. It's not going to be too good, but I will try to draw this as best as I can. I have this surface S. I have this curve C here. And I have this surface S. Now, that I'm bounded by. It's some 3-dimensional surface. It can be going all over the place. It doesn't have to be flat, which in this case is not flat, for instance. Let's assume then that I have a normal vector. S has a normal vector. S will have an orientation. What I mean by an orientation is that we always have two normal vectors. We either have one pointing upwards or downwards. Right? We have two sides to every single normal vector, one pointing in, one pointing out, something like that. Something like this. Maybe I have a normal vector like this, right? Now, what do I mean by positively oriented curve? Well, it has to be related to the normal vector itself. So what I want you to do is think about the right-hand rule here, okay? The right-hand rule means that as I curve my curve, as I go around my curve, whichever direction's around my curve here, I have to be following the right-hand rule. And my normal vector has to be pointing in the direction of my thumb. So in this case, if my normal vector is pointing up this way, I kind of use the right-hand rule, and I realize that in order to use my right-hand rule, I need to be oriented in this direction. Because if I curve my hands like that, the normal vector has to be pointing upwards. Now let's assume that I picked the exact opposite one, and I kind of went downwards. This is my normal vector here. I see that my orientation has to be kind of this way, and I kind of point my hands downwards. So I would have to go in this orientation here. I hope that makes sense. Another way you can think about it too, this is the way I kind of like to think about it in sometimes the normal, like right-hand rules is a good way of doing it. Another way you can kind of think about it too is if I'm a person standing on this curve and walking, if I'm walking in the direction of the curve, if I turn to my left, I need to be seeing the normal vector. I can't see below the surface. I have to be seeing the normal vector immediately. So here, if I'm walking in this direction, right, if I'm walking in this direction on the curve and I turn to my left, I need to be looking into the domain, which I'm looking into the domain, but I need to be able to see the vector itself. I need to be able to see the normal vector. In this case, I'll be able to, but I won't be able to see the normal vector downwards. So that means I'm in the same orientation. And similarly, I could be facing in the exact opposite way here and going in that direction. And now if I turn to my left, if I'm going in that direction, right, now I can actually see the normal vector here. This is what I mean by positively oriented. So we have an orientation that is required of it. So let's assume now that I have this n. This n here is the normal vector with proper orientation of S, proper orientation. And what proper orientation means is just, am I oriented correctly? Is the C and the N properly oriented combination? You know, it's okay if it's, I mean, you have to just be careful because if it's not, right, everything just gets negated. Right, so again, how much work does it take to move an object around a curve? And what this says now, what Stokes Theorem says, and this is the really important part of Stokes Theorem, is it says that we're able to calculate this work integral here. If all of this is satisfied, the PQR have to have those same continuous and on my surface S, it has to be continuous, or we still have that property. But what we can say is I can actually take that curve, whatever that curve is bounding, and take that surface, whatever that surface of the boundary is. Now, what's really, really impressive is there's many different surfaces with that boundary. There's many different surfaces. For instance, I could create something, maybe something like this. Right? Maybe something that's something like that. This surface, maybe there's something that's kind of over that, like a paraboloid almost, that has that surface. Same exact thing. So it could be any surface that has it, any. And that's a really, really important fact that we'll talk about. But this is something, it could be any surface it has. And what we can say here is I can calculate the amount of work it takes and relate it to a surface integral. But what we have to do is this surface integral, right? We have something like f dot ds a lot of times, right? This kind of surface integral. What we'll say here is this is actually the curl of f dotted with that normal vector ds, which again can be written in a more succinct tone as this. And this right here is Stokes' theorem, as I just kind of move that over there. And this is Stokes' theorem. Stokes' theorem says I can find out how much work it takes for me to move an object around a closed curve in 3 dimensions, right? And relate it to just any surface that has that, and related to a flux integral, kind of this idea of a flux integral with this vector field f now being the curl of f, and this n being the normal vector pointing in the exact direction that we need it to, that's related to the right hand rule. And with that in mind, we actually do have some really interesting properties here. Now thinking about, I want to kind of show you something really quickly. Let's assume that I only have a p and a q. Okay, let's say I only have a p and a q. Let's say I'm only in a two-dimensional case, right? Let's say I have, I have my vector field that is something like p, q, and 0. It has no z case at all. It has none. Well, what happens here? What does my vector field become? Right? What does my vector field become? Well, if I kind of do this, my vector field becomes this, and maybe these are not dependent on z at all, right? F is only dependent on x and y here, and it's not dependent on anything. That's just dependent on x, p, q, and I have this 0 now. And let's say my surface is like flat in some way, right? It's not dependent on z at all. What's really interesting is this curl then becomes, well, this r here is a 0, because this is 0 here, kind of putting this here, that's a 0. This qz, I mean, z is not dependent, this q is not dependent on z, so this entire thing is 0. This entire thing will become 0, and I'm just left with the curl of f being equal to 0, 0, qx minus py. And we know where that's from, this qx minus py, and we know where that's from. And any single system just on my xy plane, if this is all on my xy plane here, I know if I just have a surface on my xy plane, the normal vector to that surface has to be in the positive z or the negative z direction, right? If I just have a flat surface on my xy plane, it has to be either one of those directions. So when I take the normal vector of both of these, I'm just going to pop out the qx minus py and relate it to the domain that I'm integrating around on my domain on my xy plane. And so what's really interesting is that Stokes theorem is just the generalization of Green's theorem. Green's theorem is a very specific case. What Green's theorem says is if I have a two-dimensional case, the curl of a vector field f becomes very simple. Just 0, 0, qx minus py. And the normal vector becomes very simple because it's just 0, 0, 1 or 0, 0, negative 1, kind of going upwards or downwards, depending on the orientation of C. And so because of that curl, the Stokes theorem is the much more generalized version of it. So that's kind of cool. I mean, it's again in a different way for me to utilize, this whole aspect of how do I solve this integral of over f dot dr, right? How do I solve this work integral? It's always relating back to a surface here. So with this all in mind, I've talked a lot already about this. How do we actually use this in practice? How do we actually go about trying to evaluate this kind of thing? So let's do a problem. I'm going to show you two problems. I'm going to show you one way that we go in one direction and then the other direction, kind of like that. These problems are usually a little bit longer. They can be a little bit lengthy, and that's just kind of how it goes, honestly, because a lot of these problems are just pretty taxing. But we're going to do some problems at least initially here. They're not extremely taxing, but at least have some properties here. How do we kind of go about these? So the problem one that we'll first do here is we're going to try to evaluate this f dot dr here, where f is equal to negative y squared x z squared, something like that. And c is the curve of intersection of the plane y plus z equal to 2, and the cylinder x squared plus y squared is equal to 1. Okay, so let's first off draw this out as best as we can. And again, we're not going to be able to draw this really well. It's not going to be perfect. I promise it's not going to be perfect whatsoever. And I do not claim that it's going to be perfect, but I will at least try to do something like this. So we have our cylinder. Here we have our cylinder kind of going up like this. Boop, 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 something like that. Now, if I try to draw y plus z equal to 2, something like that, well, I know it's going to be kind of coming in like this because y plus z equal to 2. It's like z equals 2 minus y. So it's going to be coming in maybe some direction like this, like that. That's going to be like this plane. It's going to get cut across. It's going to cut across like this direction. It's going to cut across in this direction here. And we kind of see that what it's going to be. It's kind of going to be this ovular shape. It's kind of this curve of intersection. I hope you'd agree. It's this ovular shape, and we'll call this a curve C. And we're told in the problem that this curve moves counterclockwise. Okay, so this moves counterclockwise. Counterclockwise when looking down. So when I look down at this counterclockwise, if I look down on it, kind of looking from a downwards perspective, it's going to be moving counterclockwise, which we kind of think about from the y-x plane, right? From the y-x, if I look down on it, we're going to have to lose counterclockwise, so it would move in this direction here. Okay. Okay, so now, with this in mind, well, what I could do, if we did not have Stokes' theorem, think about what I would have to do. I would have to first off parameterize this curve C. Right? To parameterize this curve C, might be a little bit difficult to do that. What I could do is, again, I might be able to try to figure out a way. Maybe I have cosines and sines, right? That could be something I could do. That could be something I could definitely do here. I could use cosines and sines. I would then have to kind of do this. I would have to parameterize this. I would have to then, compute f of r of t, right? Kind of go through that, parameterize that, go from there, and evaluate it. That may be a little bit taxing, honestly. We could see at least the process what it would be, but it may be a little bit long because it's not a really, really nice one. So what we want to do is, if we were going to utilize Stokes' theorem, our goal is then to find a surface with this boundary of C. And I think probably the easiest boundary is a surface is just the part of the plane that's inside the cylinder, which has this. So it's this surface right here. It's literally just that surface, right? That surface here, this surface, I will call this S. The surface S has the boundary of C. Boundary of C. Okay. Now, if I'm going to try to have this be an orientation that's positively oriented and kind of fit orientation, we see I have a counterclockwise direction. So to have my right-hand rule, I will need a normal vector pointing out in this direction here. Agreed on that? Okay. So in order to now do this, to kind of work with this here, what we're going to do is we need to now, we see we have this surface S. We have this orientation, we call this n, or this normal vector n. And so we can utilize Stokes' theorem here. And what this says, Stokes' theorem says we can convert this integral now into a double integral over my domain S, over this surface S now, of the curl of the vector field f dot ds. Now, how do we actually go about calculating an integral like f dot ds? If I just had this f dot ds, what do I have to do? I have to parameterize my curve, my surface now, with respect to two variables, u and v. I have to calculate my normal vector, which sometimes is very simple here. It actually might not be too bad, kind of working with that. And then from there, we have to kind of just take the dot product of that and take the cross product of my parameterization, right, to find my normal vector, and go from there. It's the same process, but now we just have this weird vector field. So a couple of things to kind of go for a process here. This is at least my opinion if I first have to do it. So the first thing is you have to identify a surface S, right? You have to identify a surface S. So identify and parameterize a surface S. Now, honestly, there are infinitely many surfaces with such a boundary. And that's what's really important about this. There's not one single surface you can use. It just has to be a surface. And you want to just pick the easiest one for the problem. Sometimes that might be a little bit complicated to figure out what's the easiest. But at least pick the most normal one. Pick the most obvious one, honestly, at first. And if you need to pick a different one, you can. Like, you can go to a different process. but you want to identify to parameterize a surface. So this is my surface here. So let's parameterize this surface. Well, let's think about what I want to use. Well, what is this surface specifically? This surface, I hope you'd agree, is just the plane. It is just the plane. It's not the cylinder. The surface is the plane y plus z equal to 2. And so this, one really quick way of trying to parameterize this, I think is pretty quick, right? Is to notice here that you have, you can write this plane, use z here, as z is equal to 2 minus y. So realistically, you could do something like r of xy is equal to x, y, 2 minus y. I think it's a pretty simple parameterization. The thing then becomes, unfortunately, here, that when you try to parameterize this and you kind of go down like this, x, y, and we see this domain here, it's not as nice because it's actually a circle. Because if I'm trying to figure out my parameterization, I project onto the xy plane, and the projection is going to just be the cylinder. If I look down on it, it's going to be just this cylinder, which will be the circle on the xy plane. And so if I want to see this, I probably should maybe parameterize this in terms of, in terms of cylindrical coordinates, which might not be a bad thing. So instead of this, I'm going to parameterize this surface. I'm being very bad at moving my domain here, my thing here. Instead, why don't we use r and theta? All I'm going to do is I'm just going to change every single one of these parameterizations to r cosine theta, r sine theta, and r sine of theta. Now you might say to yourself, well, Nick, I don't want to do this. I mean, totally okay if you don't want to do it. Honestly, it's totally okay. You can leave it as xy and 2xy. You can have your domain like that. And then once you kind of do the curl and all that and work with it, it's okay. I mean, it does not matter. You can work with either one. I personally like to do it immediately off the bat and then kind of work with there. But at this point, I'm just going to go work with this here. My domain then becomes r from 0 to 1 and theta from 0 to 2 pi. This also prevents me from not having to, pay the price at the end and change it from r dr d theta. Because if I already have it like this, I don't have to worry about that. I don't have to come back and remember to do r dr d theta. I don't have to do that anymore. I've done this and I'm done. I kind of already go to cylindrical. I already go to that method. I already go to r and theta. I don't have to change it. And that kind of makes me a little bit happier in the long run. So now, thinking about what I need to do, right? How do I actually evaluate this, right? Now I have my domain D here. This is my domain D over here. I would need to, curl of F, evaluate this at R of UV, and take the dot product with my normal vector, RU cross RV dA. Right, this is my goal. I need to now compute the curl of F with respect to my variables R of UV, and then take the cross product. So since I already have this, I'm going to take the cross product of these right now, and go from there. So that's at least what I'm going to do first. You can take the curl and then go from there. Sometimes the curl of a vector field is really nice. Sometimes you maybe want to just even check. Actually, it might not be beneficial to do this because if the curl of the vector field is really nice, if it's 0, the answer is 0, right? So if it's a 0 vector, it's 0. So why don't we just check the curl of the vector field? Let's do that problem. I'm going to calculate the curl of F. So to calculate the curl of F, we're going to set it up this way. So the curl of F, or written as this cross product, which is the del operator, which is just the dx, dy, dz kind of things, the partial with respect to x, partial with respect to y, partial with respect to z. Crossing that, it kind of looks like this cross product here. That's why we can write it as this form. Y, z, p here is going to be negative y squared, x, z squared is z squared right there. Okay, so now let us try to calculate this curl. To calculate this curl, the I component is going to be, I'll write this out very formally just so we can see this, it's going to be the derivative of y with respect to z squared minus the derivative of z with respect to x. When I'm doing the derivative of that with respect to that. Then next here, the j component is going to be the derivative of x with respect to z squared. Derivative of x with respect to z, derivative of z squared with respect to x minus the derivative of negative y squared with respect to z. We see that a lot of these are going to be 0. And lastly here, with respect to k, this next one here is going to be the derivative of y with respect to this, the derivative of this guy, so dy. Oh, we actually have to compute a derivative, yay! Minus d dx of x. And so what we can get here, if you see, this first component is going to be 0. The second component is going to be 0. And this third component here is going to be negative 2y minus 1. And this is the curl of my vector field. I mean, that's not too bad at all. Now, what does this curl mean again? The visualization of this curl means that if I place any object, if I place an object in this vector field, I place, let's say I'm at some point, I plug in my points for this, I get a normal vector like this, and again, we'll talk about the rotation, what axis am I rotating around? Kind of it relates to the rotation here. And so we can see here that the rotation always will be only in the z direction. I'm rotating around the z direction. That means I'm always going to rotate a parallel to the xy plane. Kind of a weird thing with this vector field. But again, the vector field and the surface are different. Right? They're completely different here. They're independent of each other. Okay, so now we have this curl. All good and well. Now what I'm going to do is I'm going to calculate the curl of f at this exact parameterization. I'm going to use this parameterization here to kind of evaluate that. So I'm going to now calculate the curl of f at r of r theta. It's a weird thing to kind of put, I know. R theta, I probably should not use this, it's not that. And now we see it's going to be 0, 0. Well, my parameterization then becomes here, well, this is going to be negative 2y minus 1. This y is just r sine of theta. So this becomes negative 2y, negative 2 times r sine of theta minus 1. Cool. That's my curl. Next thing, so this is one thing I have to calculate. And the second thing I have to calculate is RU cross RV. So let me calculate this normal vector here. I'm going to move up here just so we can kind of use I'm actually going to just keep moving down. We'll just do that and then we'll zoom out here. So what I'm going to do now is I'm going to calculate RR and R theta. So RR here, as a reminder, oh, that was bad. Sorry, did not mean to do that. Cool. Thank you for seeing my entire screen. RR here. So we see that we're going to have, right, we have the cosine of theta. We just calculate this. This becomes cosine of theta, sine of theta. And then over here we get negative sine of theta. Cool. If I'm taking this with respect to theta, this becomes then negative r sine of theta. This will become just r cosine of theta. And lastly here, this becomes just negative r cosine of theta. And now we take this cross product here. So you can see these problems will start to become a little bit longer. That's okay. Let's take this cross product here. This cross product then becomes sine, so it'd be negative r cosine of theta, sine of theta, plus minus a plus, right? We would get something like that. I would get r cosine of theta, r sine of theta. I hope you see that's probably going to be 0 because we're canceling out, which should make sense because the normal vector of this surface, it's not dependent on x at all, right? If I'm looking at this, it should be kind of like 0, 1, 1, right? It should be kind of going in that direction. So we kind of make sense there. Oh no, did not mean to do that at all. I meant to move everything. Sorry. Sorry, everybody. My iPad is not helping me today. Well, I'm just not doing very well. So then what we're going to do is we have this minus sign here out in front. We will then take negative r cosine squared of theta, and then minus, it would be a minus, yeah, we got a minus, it'll be good. So r sine squared of theta. Cool, that's going to just be r. That's all nice. And then over here, we're going to get r cosine theta times r sine theta. Again, really, really nice. Cosine squared of theta plus r sine squared of theta. And so we actually get a really, really, really nice normal vector of 0. This will just become r, and this will become r. And that's my normal vector. Okay, so now I have this guy, and what we see is we're going to take the dot product of this red thing, and we're going to take the dot product with the 0 r here. Yeah, and that's going to be it. So after I do that, it's going to kind of be over. So we need to now compute this integral up here. And I'm going to come back over to here now, move myself up here. And now what we're going to get is we're now going to take this integral here. We're now going to actually evaluate this. So the integral will become the following. It's 0 to 1 and 0 to 2 pi, which is my domain. We're now going to take the dot product between this vector right here, this curl of 0, right, this curl of my r of uv, 0, 0, negative 2 r sine of theta. So it's going to be 0, 0, negative 2 r sine of theta minus 1. Taking the dot product with 0 r, which is my normal vector. This is my normal vector to my surface. Now we just want to make sure before we actually start going, and this is actually a really good thing to check. It has to make sure that we're actually orienting this correctly. Are we pointing upwards? I need to be pointing upwards here. If I'm not pointing upwards, I need to flip it. In this case, r can't be negative, so the z component will be positive, which is good. So that means that I am pointing in the correct direction to have my orientation make sense so I can utilize Stokes theorem here, which is good to check. And then this will become dr d theta. Now we can just evaluate this integral. As you can see, the only part that's going to really matter is the c component here, which is going to be negative 2 r sine theta minus 1 times r. So 0 to 2 pi, 0 to 1 of negative 2 r squared sine of theta minus r dr d theta. And now let's integrate this. This then becomes, if I take this integral with respect to r, right, this first one will become 2/3 r to the third, negative 2/3 r to the third sine of theta minus r squared over 2. We're evaluating this between 0 and 1. This then becomes here, right, we just plug in this 1 here, this becomes negative 2/3, negative 2/3 sine of theta minus 1/2 d theta. Cool. Now, if you notice here, the integral of sine between 0 and 2 pi is going to be 0, period, right? It's periodic. That's all really nice. So this integral will be 0 because it's periodic. And so all we have to worry about is this integral, which is just going to be negative 1/2 times the length of 2 pi, 0 to 2 pi, which is just 2 pi. So this becomes negative 1/2 times 2 pi, which is just negative pi. And that is my answer. That's kind of how you do this problem. And kind of looking back as to how we went about this, right? The process is going to be the same always when we do this kind of issue, right? So I have this integral of over c of f dot dr. I'm trying to find out how much work it takes for me to move an object around this curve c. I see it's going to be a little bit complicated to write this curve. You could do it. I mean, it's definitely possible to kind of go about doing that. And then what we see is we want to find a surface. We want to find a surface that has this boundary. There are many. For instance, you could have taken this cylinder, below, right? You could have taken the cylinder that has that. It's gonna be a little bit complicated to kind of write that, but you could. I mean, you could get the same exact answer if we did it. And then what we have to do is we have to make sure we're going in the right orientation. We need to find a parameterization of this surface, right? To kind of evaluate this, we need to find the parameterization of it. And then what we do is we go from 0 to 1 and theta being 0 to 2 pi, we see that's probably a little easier to do that way. We then calculate the curl of f in this form, finding that we got this answer here. And then, understanding that we have to take our normal vector and then taking the dot product of these two things here, and then integrating it out. So it's the same exact process as always, right, to evaluate this kind of integral. This curl of f is just a type of vector field. So it's the same as f dot ds. So it's the same process. It's honestly the exact same process as we did last chapter. However, I'm just doing it with a different vector field. It's just curl of f now, nothing else. Kind of working with that. Okay, so that's at least, and then we kind of just integrate this out, we get negative pi, which means it takes the amount of work it takes for me to move an object around this vector field, around this curve C through this vector field, it's gonna be about negative pi. So I'm gonna be going against the grain a lot in this direction. Okay. So that's kind of Stokes theorem here. Stokes theorem, I think the most difficult part many times is kind of just, really coming up with your parameterization, coming up with a good surface sometimes. I mean, many times it's not too bad. You might want to just make sure as well that I think the biggest thing that trips people up when you're doing Stokes theorem is to make sure that you're going in the correct parameterization. Use the right-hand rule and negate everything if you kind of find out that at the end you messed up. You're like, oh, I'm just going to negate everything. It's not too bad to kind of do that. And sometimes it's a lot easier, for instance, to go backwards. So if I'm actually evaluating the curl of f dot ds and I'm evaluating that kind of integral, you can use the Stokes theorem going the exact opposite way, where you can find a curve and you can just utilize that curve, and maybe that's a really much easier thing to do. Sometimes there's problems where we'll do double integrals, where, for instance, where we can use Stokes theorem maybe twice to actually exchange from maybe evaluating a vector field over, some interesting surface. We can find that domain, we can find that boundary, kind of find a boundary, and then actually integrate it over the next domain. Because of the following, let me show you something really quickly. Let me just draw this out and then we'll stop with this video for the moment. Because these problems are really taxing. And honestly, they're a little bit long, and many times, I know, at least from UD, they're not going to really ask too many questions about them, if any. But I wanted to show you something. So if I have this surface S1 and I want to calculate the curl of f dot ds, if I wanted to calculate this integral, one thing I want to show you is if I have some surface here, I don't know, let me just check, something like this here, woof, woof, woof. Some surface like this, and I want to calculate this surface. This is my S1, this entire surface up here. Well, what we could do is if I wanted to instead, I have this weird surface here. I could, let's say it's positively oriented like this, right-hand rule, I could just evaluate this curve C. Right, so I could then say to yourself, oh, okay, well, this can just be calculated as using Stokes theorem, something like this. But then maybe this curve is a little bit complicated. I don't know, maybe it is. Or maybe there's just a really easy way to kind of do about it. But what we see here is there another surface with that exact boundary? And we note that, for instance, this bottom part has that boundary. We'll call this S2. So what's really interesting is we can use Stokes theorem again. And what's really interesting here is this shows surfaces have the exact same boundary. We actually get that this integral, the curl of f dot ds, is equal to the curl of f dot ds over that other boundary, over that other surface. So if two surfaces have the same exact boundary, what we can do is we can utilize Stokes theorem twice, which is pretty remarkable. Honestly, and we can get to this kind of form. So we can even utilize, try to figure this out, kind of going from there. again, what the idea of Stokes theorem really is trying to say here is it's a way for us, and Green's theorem, just in a way for us to relate, the boundary of a surface, to the surface itself. And this is really a fundamental part of just calculus in general. As we thought, fundamental theorem of calculus has that, right? We have the boundary related to the other boundary. Related to, the integral of f prime is really just the evaluation of the antiderivative at the end and the beginning, right? Trying to relate those things, relating derivatives, relating just regular continuous functions with their boundaries and their domains. And so this is basically the idea of Stokes theorem here in a nutshell. I know that we only did one problem, but as you can see, these problems get very, very lengthy, unfortunately. We can go backwards and forwards in many different ways. And so to kind of just recap a couple of things here. Firstly, if you are trying to find if a vector field is conservative in 3 dimensions, we have to satisfy all these 3 things, which also is the same exact thing as saying the curl of f, this value right here, this vector, has to be 0. So we see that the curl of f at being 0 is just equal to the f being conservative. Same exact thing. We then want to try to see, how do we evaluate this work integral in 3 dimensions? Is there a way to do this? Is there an extension of Green's theorem? And yes, there is an extension of Green's theorem. It's called Stokes theorem, which allows you to calculate this integral utilizing, a flux integral, basically, with this curl of f as your vector field instead. You do have to make that change. In the same way, we have this qx minus py, which actually is saying that Green's theorem is just a special case of Stokes theorem in general. And we did a problem here. Right, we saw that I have my vector field f. I have this vector field f. I want to try to find out how much work it takes to move a closed curve around a closed curve, and we can kind of work with this, right? We parameterize our surface S. We find a surface S first, identify one. We then take the curl and evaluate the parameterization at that vector field. And yeah, I'm actually realizing now. I think I'm realizing now that I made a mistake here. I think this should be 1 minus 2y plus 2y. Oh my gosh, yeah, that's actually really bad. I'm so sorry. Most of you must be really, really confused about that. Yep, I'm sorry about that. This should be, if I was to actually do this correctly, my gosh, I made this completely incorrectly. Wow, that's horrible. Sorry about that. So this should have been the derivative of x with respect to x minus negative y squared here, which should just be 1 plus 2y. So this whole thing would become positive then. Yeah, so in total, this entire thing should be positive. That. Sorry about that, everybody. I am so sorry about that. That's pretty bad. I messed up that minus sign there. So there should be a positive pi there. Apparently I mess up sometimes with cross products here too. I thought that looked weird for a second, but it's okay. So it sometimes happens, but just make sure at least here that I have this curl of the vector field. It's 1 plus 2y. My bad there. Yeah, okay, so well, unless we fix that here, we always make mistakes. It's okay. We can fix it later. And so that's kind of the issue with this, making sure we take the curl of the vector field, making sure we plug in our parameterization correctly here, and then, finding my normal vector, and then, just taking the dot product and evaluating from there. Okay, I'll stop from that point. I hope you're doing well. I hope you're staying safe. If you have any questions, let me know. And I'm sorry about that mistake that I realized at the end there. Yeah, enjoy the rest of your day, and I'll talk to you guys soon.